Okay, let's see what time we have. Great. All right, well, welcome everyone who's joining us now. We're going to wait maybe one more minute because it seems like a lot of people are joining. We'll get started momentarily. All right, well, welcome everyone. I am Danny Kincaid. I am the current president of the AGU Informatics section. I am joined today by my section president-elect, Chris Arizaeus. And we want to welcome you to the AGU Informatics section Greg Leptoukh Lecture Award and presentation by Dr. Rahul Ramachandran. Many of you in the informatics section are aware that this award is usually determined in the fall of the year, and the award recipient gets to give their lecture and presentation at the annual meeting. Unfortunately, this past year, we weren't able to bring you Dr. Ramachandran's talk, but we're so very pleased that we have been able to reschedule and bring him to you live today. The rest of your time with us will go with me handing this presentation off to Aaron Robinson of Metadata Game Changers and also former executive director of ESIP. Aaron was our 2020 Leptoukh Lecture awardee and is the current committee chair, the selection committee chair. So she's going to say just a few words about the award. She'll pass it off to Manil Maskey, senior research scientist with NASA, who was also Dr. Ramachandran's nominator. So we want to acknowledge and thank Manil for his effort in acknowledging his peer and a former informaticist for their contributions to our field. So I'm going to stop here. I'm going to thank you once again for joining us in honoring Dr. Ramachandran and pass it over to Aaron.
Thanks so much, Danny, and thank you all who are attending. This is a great turnout. And as Danny said, my name is Aaron Robinson, and I am the current chair of the Greg Leptoukh Lecture Selection Committee, and it's my privilege to introduce the award and share a bit about Greg before I hand it over to Manil. So the Leptoukh Lecture honors the life of Greg Leptoukh, an earth scientist who worked at NASA and was active in the informatics community, both through AGU and through ESIB. He worked on projects primarily related to data quality and data provenance. And I was fortunate to overlap with Greg early in my career when I was focused on air quality. I, along with many others, have benefited from his work on Giovanni, which is a platform that's still in active development today. And now that we're just over 10 years from the initial Leptoukh Lecture, which was given in 2013 by Simon Cox, I wanted to share a bit about Greg's work and give a sense about how his legacy relates to the lecture. I recalled a present, this is the share screen nervous moment of my talk. I recalled a presentation that he had given in 2011, where he had shared a bit about this work on the multi-sensor data synergy advisor. I'm only going to show 2 slides. So this first slide is a normal NASA quad chart, but gives you a sense that he was looking to add semantic technology to Giovanni in order to encode rules that the scientists knew so that the inner comparisons that Giovanni could do would be meaningful. And I just want to point out here that it was a TRL level 2, which for those of you that don't speak NASA, that means that this was a very conceptual project. The second slide I want to show is this one, where Greg called this the Giovanni way, but really I think about it as the informatics community way. All of us here have worked to reduce this time to science and to minutes and weeks. And I think that Rahul is really going to touch on that today with the reflections that he has on how we go from petabytes to insights. So with that foundation, I'm going to stop sharing here. With that foundation, on the lecture, this is the foundation on which the lecture sits. It aims to highlight the transformational impact of computational and data innovations on scientific breakthroughs and encourage ongoing excellence and contributions to the broader informatics and data science fields. The Leptoukh Lecture, it's held each year, honors those in our community like Rahul who have continued this work and made notable achievements in informatics, computation, or data science, and those contributions can encompass research, education, and community engagement endeavors. There are many worthy candidates in our community and on this call, and I hope with this background that you'll appreciate what a special award this is. It's our one named section award, and I want you to keep this in mind in future years. So Krista is gonna add the information for Alexei Shklovanov, who is the canvassing committee chair, and also some details about other awards that the SE section or the informatics section is eligible for. So given all of this context, I'm pleased to introduce this year's lecture nominator, Dr. Manil Maskey. As Danny said, Dr. Maskey serves as the Data Science and Innovation Lead at NASA's Office of the Chief Science Data Officer, and he's also a Senior Research Scientist at Marshall Space Flight Center. Manil is an active contributor to our community and we know him well, but in this moment I want to echo Danny in thanking him for taking the time to do the nomination work. So with that, Manil, over to you.
Thank you, Erin. Hello, everyone. It's a great honor and privilege to introduce Dr. Rahul Ramachandran. He's a visionary scientist, a pioneering research, and a great mentor. And above all, his latest achievements in terms of managing these large-scale projects. So today we are here to honor his significant achievements as he receives this award. Today we are also here to hear his lecture where he will share his take on the fundamental shift in science data stewardship and analysis. So having had unique opportunity to work alongside him for what, maybe 22 years, I think, long time at the University of Alabama in Huntsville and in NASA, I can say I've witnessed firsthand his incredible journey as a mentor, as a colleague, as a project manager, and above all, as a friend. Rahul's career is a remarkable one with degrees in mechanical engineering, atmospheric science, and computer science. His early work actually laid the foundation of some of the advancements that we've seen in analyzing and managing big Earth science data sets. Another remarkable characteristics of Rahul is this sustained approach of doing things in the open. He truly has defined how we should do open science within NASA. And it has resulted in many open source software, open collaborations, and even partnerships with external entities. So just to give you couple of examples of the projects, I worked with him when he led this project called Glider, which transformed how we visualize and interact with satellite imageries. I worked with him when he was pioneering data mining tools for scientific applications. I also worked with him when he co-led the Cumulus project, which is a cloud-native data ingest and archive system, which is still the backbone of our data transition to the cloud. I also worked with him on the project called Dark Data, which we were not the first group, I think, that actually used this new deep learning techniques for science problems. And therefore, I can truly say that I know him as a source of new ideas for everyone around him. His work has not only earned him many awards, as you might have seen from his bio, including the Presidential Early Career Award for scientists and engineers, but also he has earned the respect of global science community and informatics community. During this 22-year period, for a brief 1-year period, he actually took a new challenge and left NASA, and at that point, the University of Alabama in Huntsville, to take a challenge at DOE. And one of the nominators for this award was came from DOE, and the amount of legacy he left there during that short period of time. He developed this framework called Bioenergy and Knowledge Discovery Framework, which is still being used and highly touted within DOE. And during that period, I always hoped he would come back, which he did. And that's when he came and established this project he's currently managing called Impact within NASA Marshall Space Flight Center. In his current role, he continues to push the boundaries, embracing cutting-edge technologies to improve processes and advance the scientific knowledge. Above all, what sets Rahul apart is not just his technical expertise, but his remarkable ability to mentor. As a mentor, he has had an impact not only on me, but also many others who have gone on to do bigger and better things and become successful professionals. So Rahul's vision for and future for earth science informatics is a world where technology and computational capabilities can be seamlessly infused to advance data stewardship, knowledge extraction, which echoes the essence of the Leptoukh Lecture Award. Much like Greg, whom I had the privilege of knowing for a little bit, Rahul's career is a testament to his dedication in enhancing the accessibility and deriving insights from Earth observation data for all. So before I hand it over to Rahul, I'd like to share an anecdote that seems to happen frequently, at least in the NASA circles. As I mentioned, I've worked with him for 22 years. As a result, many have mistaken me for Rahul, and vice versa. I've always considered it to be the highest compliment. I don't know if the feeling is mutual there, but having worked together with Rahul that long, of course, we've shared many common views, but there are also numerous times when we have disagreed on things. As a matter of fact, it just happened a few days ago, but I should know by now, always he's most of the time or always correct. So on that note, please join me in congratulating Rahul. Rahul, the stage is yours.
Thank you, Manal. That was a really nice intro. It's been a privilege of mine to work with you too. In fact, nowadays, people call me Manal. I think you've gone and established yourselves way beyond that, what I've done. So I think that's tremendous credit to you. So first of all, thank you all. It's an immense honor to be getting, to be nominated for the Leptoukh Lecture Award. It's to be nominated by your peers is the ultimate honor in any field. It's better than getting nominated for an award by your management who never understand what you do. Having your peers recognize what you do, I think that in the end is what really matters. I had the privilege of working with Greg. We worked during our ESIP days on semantics, metadata. I still remember Greg. Greg was, like all scientists, very skeptical of new things. He would want facts and actual, data before he was willing to change his mind. So that's one thing I remember about Greg, from our interactions early on. You all can see my screen, right? You can see the slides. Can you hear me?
Yes, Rahul, but some attendees are saying that the audio is not as clear as it could be. I'm wondering if maybe it's just a proximity to the mic for you.
Okay. Maybe I'll try to speak a little louder.
Okay, thank you.
Thanks. So I would like to start my talk here with some acknowledgements. So I think the first acknowledgement I would like to make is my parents. As Danny mentioned, I was supposed to give this lecture in December. My father fell ill in October, and I had to rush back to take care of him. He went in and out of hospital for a while, then he passed away in February, and so that was a big loss for me. My parents have an immense role in guiding me in terms of giving me the freedom to choose the path I wanted, never really worrying about what needs to be done. It's basically finding your own path in life, always being supportive and inculcating the right values in you. And I cannot thank them enough for how they raised me, especially my dad. When my dad was in hospital, I was talking to him, and my mother had mentioned that both my parents are artists. My mother told me one time that everything that she learned about art was from him. And I mentioned that to him when he was sick, and he laughed and he said, I did not teach her anything. I mean, my mom, and she learned more from my dad than any of her teachers at art school. My dad was like, I did not teach her anything. I just helped her unlock her mind. And that one sentence has stuck with me for a few months now. And I finally have truly understood the meaning of what he really meant, And it has made me realize that even my mentorship has not been enough. I think what he really meant was to really mentor and be a true teacher to somebody is not only give them the knowledge that you have, but also help them overcome the limitations that they have in their own mind. I think it's an amazing thing. I mean, that's a true legacy of a teacher and a mentor. And I hope to do better in terms of mentorship, going forward. I'm going to miss him. I mean, these are the little nuggets that I would gain from him. I'm really going to miss him for the rest of my life. I would very much like to, acknowledge that, this award and this honor goes to everyone that I've worked with. It's my whole team here, all my colleagues, my collaborators over the years, my teachers, my mentors, the students, program managers who never get any credit, even though they're supportive of, funding you for your projects. I think this honor I share with them. I think in data science and informatics, I think we have to be realistic. It is about teams who work together that produce, useful, valuable things. It's not about individuals. So I want to acknowledge that, all of them get credit for this particular honor. So I've talked about three things in my presentation here. I'll talk a little bit about my journey. As Manal was mentioning, there's a whole long list of projects I've worked with. I don't want to go through all of them. I'll just touch upon a few of them. Then I'll talk about, the problem that we've been trying to work on. I think at least most of us here is looking at scale in science, especially in earth science. How do we keep up with scales of volumes of information? And then maybe look forward a little bit in terms of we are at an inflection point and how we can approach this problem in maybe a different way that requires a change. It's not always about technology, but it's all a bit about mindset change and how we adopt and utilize it for not just tools, but also processes. So this is my journey in a nutshell. My undergrad I was actually in mechanical engineering. I thought I was going to do industrial engineering. I came to US to do industrial engineering, but after taking a few classes in industrial engineering, I did not like it too much. And then I got an offer to join a metrology course in South Dakota, which was really interesting. I mean, the professor there sent me to the library and said, go read this book by Holton on dynamics. And I looked at the book and I went through the few chapters, and it was very similar to what I had done in my undergrad. It's fluid dynamics, but it's applied to a sphere. So it was something that I could relate to really easily. So I decided to switch over. That's when I switched over to metrology, atmospheric science, who's doing research in atmospheric science. Those days, things were very difficult. You had limited amount of computing. You had old PCs with limited memories. You had very little documentation. There was no Reddit Stack Overflow to find problems. And, here you're trying to load large amounts of data into your machine to do analysis, which was very hard to do. So it was a struggle. And I was writing, I would say, terrible code. That's when I decided maybe I need to learn a little bit more about computer science to improve my, skill set and knowledge base. I went on to get a degree in computer science, and I think that's where the shift happened. Where I, started seeing where I could add value with my background in engineering, science, and then computer science. I then took on a first job as just a science programmer at DAC here in Huntsville, and then slowly became a researcher within the university before I joined NASA about 10 years back. So it has been an interesting journey, it has not been a linear pathway for me, but it has been a really rewarding one. Basically gone in directions that were of interest to me, and I think it has been really fruitful. So a lot of the work that I've done in R&D, I've been really fortunate to work on, different stages of data lifecycle. I can truly say that I've probably touched every stage of data lifecycle at a fairly detailed level that I can understand it well enough. I've also worked on systems, both at large-scale systems at platform levels and large-scale frameworks, but also at algorithm level development. So I've been very lucky that way to have a portfolio of research projects that have spanned this wide breadth, so that I have a very decent understanding of things at different levels. So I thought I'll talk a little bit about some old stuff. I hope there's some people who have worked with me with, when you look back, you think about some of your old projects. Some were good, some you cringe a little bit. The first one was the Earth Science Markup Language. This was when XML came into play as a technology. And the idea here was you could basically use external descriptions covering both the contextual metadata, which is like enabling search, but also defining structures within data files so you can access data in a fast manner, and then adding semantics, which was the novelty there. You add semantics so that the tools can do inferencing and do some kind of automated processing. I worked a little bit on ontologies with Rob Raskin from Suite Ontology. I was actively involved in the ECIP semantic web cluster. This was a long time ago. It was a privilege to work with Rob Raskin and Peter Fox. They were tremendous human beings. Learned a lot. That group was fantastic in terms of the intellectual clout and weight that they had. It had Chris Linus, Hook Hua, Brian Wilson, immensely bright people at a completely different intellectual level than me. I learned tremendously from all of them. I worked on Noises, which was basically a search engine, way maybe a little ahead of its time, trying to use ontologies to enable search across different repositories. Data Album, which was an AIST project, AI Access project actually. I was trying to curate data set and information in an automated manner. When I joined NASA, I was asked to lead the data curation effort for White House's Climate Data Initiative. This was during Obama's administration. It was a lesson in learning how to manage people across different organizations, because there was a lot of effort trying to work with other federal agencies to put together, curate and put together their metadata in a manner that could be useful to the climate community. Well, the recent work in this area that we've been exploring as a team here at Impact is this notion of a modern data governance framework. Is maybe can we simplify how we manage our data? How do we govern our data? And let's not make it overcomplicated, given the scales of these data sets are always increasing. Some examples of my work, on analysis and data platforms. I think the first one is the Atom, which was a data mining. It was a system and then became a Python library that was developed by John Rushing, an immensely bright colleague of mine, who developed this tool which was fantastic. It was, it had amazing capability of applying data mining algorithm to data set. We leveraged that tool to build applications and to support science. We also then converted those libraries to web services, including building a collaborative workflow system called Leptoukh, where people could come and work together remotely and build these data flow pipelines for data mining. I was lucky enough to be part of a team on a large NSF infrastructure project called LEAD. It was based on pre-cloud technology. It's called grid computing. So it was really interesting to work on that project to see how you could scale up computing and leverage distributed computing across different research centers within NSF infrastructures. When I was at Oak Ridge, as Manal mentioned, I led this creation of this bioenergy KDF, which is used to support biofuel research within the US and support the industry there in terms of both modeling data and also all the knowledge that is in papers and reports that need to be curated and made available to the community. Recently, with the team here, we worked on things like a hurricane portal, which is based on AI, trying to predict wind speeds. We looked at similarity searches based on images, where we can actually allow people to find satellite images that look similar rather than doing word text-based queries. So over these years, it's been really interesting. I thought at least I'd share at least 3 of my thoughts of things I've learned, going through all these years, working with so many people, learning from all of them. I think the first thing is, I think no knowledge ever goes to waste. Everything you learn is useful, you just don't know it. I'll give you a really concrete example of this. When I was in my undergrad, I did an internship at Toyota building light commercial trucks. And Toyota at that time was pioneering this notion of management called Kaizen. It's just-in-time inventory. It's fundamentally everything that agile methodologies are based on. I had no idea until you come to software engineering and you start seeing the same concepts being applied there. So it is interesting to see that things that you think that are insignificant become significant later in your life. Second thing is the advice I gave to a lot of people and younger colleagues in my team that, I think just as a tree needs a suitable environment to grow, people need suitable environment to thrive. So you have to find your own fit. You have to find an environment where you can grow, you'll be nourished. I think that's really important. And if you are in a leadership position, I think it's your job to make sure that you provide an environment for other people to grow and be effective. And I think the last thing is, I think we tend to give too much weight to people who have the technical depth, which is great. I mean, it's great to have technical depth and to specialize. But I think there is tremendous value to be what I call a boundary spanner. Be able to span across different domains, different disciplines, connect the dots. And I think that helps find solutions when narrow focused approach may not work. So I think my career has been pretty much being a boundary spanner and encourage others to maybe also pursue similar approaches too. Okay, so that's a little bit on just the background. Now I'll talk a little bit about problem of scale. I think most of us who work with Earth observation data know this really well. I think what we are seeing is, both the volume, computational capability, the speed of research is increasing dramatically. And this is basically driving the need to, having faster scientific discoveries, needing new skills, new modes of collaboration, and creating challenges in how we manage data, how do we do governance around the data. And the scale is not just a data issue, right? It's basically also an information management and knowledge management issue. Because if you are a scientist, you have so much information, like how do you filter out what is the right thing for you? And I would also argue that the scaling is not just a technology problem. It's very much, we need to relook at processes, practices, policies for both knowledge management, data management. And these have to adapt to this changing reality of scales. So as I mentioned, this is not a new problem. This is a famous quote from John Naisbitt in 1982, drowning in information and starving for knowledge. The other quote there in the slide is from the NRC report in 1980s, where they were, worrying about all the data that's going to come from these instruments from space. How will we process them? And that challenge has not changed. It's still there. We are still facing the same problems, even though it's been 30, 40 years now. So in 2002, I think this was another report that basically talked about, the need for new tools and approaches to manage this, the scales of data, like accessing, analyzing data, recognizing patterns, performing cross correlations that are scalable. So I think this still holds. I mean, this need still holds right now. So I think this is the question we've always asked ourselves, like, what is our collective objective? Our collective objective clearly is to support science, is to basically make sure that we can help create new knowledge. But then the onus is on us, I mean, all of you here, the informatics community. How can we continuously manage the science data lifecycle effectively so that it can handle scale? How do you continuously support research lifecycle so that we can actually derive insights from these ever-growing archives? And I think for me, there's been a realization that the improvements to both the data and research lifecycle cannot be a one-off activity. It has to be a systematic, thoughtful, continuous process. It can't be like big shifts that we make. I think we have to make it into a process of just evolving all the time so that we can manage the data information in an efficient manner. So I show this figure almost all the time when I'm presenting. This is basically a very traditional view of data and research lifecycle. Obviously, data is the center of gravity for us. Everything revolves around data. The inner circle is the data lifecycle, which covers basically the stages of data, right? You have a mission that's launched, the instrument that's collecting, making some measurements. Those bits have to be converted into some meaningful scientific parameter. That's where you have your standard production generation. You go through the whole ingest archive to make the data discoverable and useful. You have to have documentation. You have to make sure that you have data available through different means of access. And you provide support on using the data correctly and effectively, right? And then you make sure you archive all these valuable data sets, which are national assets. The blue ribbon there is basically the a little kind of a quick list of tools and infrastructure needed to support not only the data lifecycle, but also the lifecycle outside, which is the research lifecycle, right? So this is kind of what the building blocks on how we support science. But I think the interesting thing is, something that made me, this is only recently I've started thinking about this, is this notion of a perpetual feedback loop that you have between the data lifecycle and the research lifecycle. You have new technology that drives new research opportunities, and new research findings lead to new technology innovations. And these have impact on both the research lifecycle, which impacts the data lifecycle. So for example, you have new instruments, new algorithms that create more data or need more complex analysis. So those all get pushed on the data lifecycle, which require better governance, better management, better processes, better infrastructure for faster access, visualization, and analysis. So the need to continually evolve and adapt and adopt new technologies, process and procedures and policies will always be there. I borrowed this quote from one of my colleagues' blog, and I really liked it. It basically says we are called to be the architects of the future and not its victims. I think that's the way we need to approach it, especially with new technology, is to see how we can shape it so that it can serve the science community. And I'm talking specifically of AI right now. I think we are at a new inflection point of AI adoption of AI within the enterprise. Right? We've seen what ChatGPT can do. We know that these things will have a major impact in both on how we manage data and how we analyze data. And specifically, the thing that I've been focusing on is this notion of foundation models, which is, I think, very much a game changer. I think it's a very much in something that is be an important component in the data systems moving forward, right? That can support both the data and research lifecycle. So, what are AI foundation models? For those of you who do not know, these AI foundation models are basically networks that are trained on vast amounts of data, and they still serve as a starting point or a foundation for applying it to different tasks and to be different categories of tasks through something called fine-tuning. So the beauty of this is that these foundation models, since they are pre-trained, which is using self-supervision, learn patterns, relationships, and knowledge that are there in the data that is used to train them. And once you train them, this one single model can then be used for a variety of different applications. And what it does is it reduces the downstream cost, both in computation to build applications for AI, but also in terms of labor and trying to build large training data sets. But the challenge here is that the foundation models are complex to build, right? And they're not easy things to build. Single teams cannot build it. You require significant resources, that is computation, storage, expertise. And large data sets and computational power are essential for pre-training foundation models. Within NASA, we have so much data in our archives that we can fully utilize to make sure that we can actually extract insights from the data. So this is the at least the current vision in terms of how we can use foundation models in both data and research lifecycle. So this is like unrolling the two life cycles. So you have upstream, you have your data stewardship and data management activities, where we think the large language models that are already available right now can play a role, but also we will see a role of domain-specific language models that can help specifically develop for science. And then downstream is building these foundation models for high-value data sets or thematic areas so that you can support large categories of problems like classification, prediction, similarity search. But it is important to know that just building the models is not enough. You also need to, for the community to adopt so that they can use the data and these models in their application, we need to also provide them with infrastructure and training for them to be successful. So I'll talk a little bit about large language models, and most of you probably know more about this now. They are obviously used widely. The issue that they have is this notion of hallucination, where they can produce wrong answers very confidently. I think there are ways around. You can get, fix that when you are building applications. It's whether you're using prompt engineering by providing context, or you do fine tuning for specific applications. The other alternative that we've been looking at is something called retrieval augmented generation, where you basically combine the language model with information database. So basically what that does is you first, based on the query, you first find the relevant documents, and then you give those passages within the document for it to generate the answer for you, so that now you have some evidence block that you can go back and look at in terms of where it got the answer. And then these models can be obviously adapted to support a wide range of data governance and management activities, search discovery, as well as making analytics really easy for end users. Some examples, this is looking at the impact of applying these language models to do some of the augmentation of processes for ingest and archive. So this is just a back of the envelope cost calculations that we did of our 13 different budget estimates that we've done for just in archive data sets. So there are 16 different steps that we go through. We identified which of these steps could be augmented by AI. And then we said, okay, if you had 20%, 50%, 35% labor savings, how much would the cost savings would be? So you get the range from 8% to 34% cost savings. So that shows the value in terms of, this is not in terms of cost saving, but you could see that, it allows you to scale and handle more data with the same amount of resources. Some applications of using a language model. I'll show you some quick prototypes. This is a demo that was put together by IBM Research. We're working with the language model with us here. This is an extractive question answering tool demo where you ask a question, it searches through all the research papers and finds these couple of sentences that closely match the question that you're asking. And it gives you this notion of evidence block so that you can know where the answer came from. So this is not generative at all. This is an extractive Q&A capability using a language model. This is a demo that my team here put together. It's showing how you can use natural language to query existing databases. So this is querying the firm's database. Where you can ask questions like how many files were there in US yesterday, and it'll go back. It'll basically take your question, convert it into SQL queries, figure out which endpoint to call, make a query for you, get the results back, and then retranslate your answer back in a form that a human can understand. So I think this is kind of where things will progress, I would say, in the very near future. So these are just examples of what can and will be done soon. So everything that I've talked about right now has been on the language model side. I now want to shift gears and talk about foundation models for science. I think the idea here is, we've had so much data in our archives. Can we build foundation models on our science data sets akin to the language models that can be used by people for their science applications, their fundamental research? So when we started, this was an initial proof of prototyping effort that we did with IBM Research. We wanted to test out this concept of geospatial foundation model. It's called Prithvi. We selected the harmonized Landsat Sentinel-2 data that's produced here. We wanted to understand, what are the design criteria for building a geospatial foundation model? What should be the evaluation criteria for building, for testing out the foundation model? What kind of pre-processing is needed? And fundamentally, is there value in building this AI foundation model? So the goal was you take HLS data, you pre-train it without any objective in mind, and build this base HLS foundation model called Prithvi, and then you can adapt it for a wide variety of problems, whether it's segmentation, adaptation, or different kinds of tasks that we can test out. So this is a little bit more deeper dive on what was done. The box on top shows the pre-training, and the way they did the pre-training is they used something called a mask autoencoder architecture. It's basically an encoder-decoder, and similar to a language, how they train a language model, which is, they will mask out a word in a sentence, which is considered a token. And the network has to predict that word back, given the context of rest of the words in the particular sentence. So similar approach is used here. So you make patches in the images. You can see those blocks, those are patches, and those are equivalent to tokens. So you mask off patches in the images, and then you feed it to the network, and it has to fill in those patches back. And you just keep giving it a lot of data, and it learns how the patterns in the data to fill the patches back correctly. And once it has done that, then you can just take the encoder model, which is your base foundation model, and then you can just add different heads or layers on top to different tasks, whether it's doing semantic segmentation or doing prediction. So the unique thing here was they used the standard VIT as a backbone, but they made changes specifically for geospatial data, that things like 3D positional embedding, 3D patch embedding to handle the spatiotemporal nature of the data. So this is, we tested this out for different use cases of this foundation model, and this is a case where it's doing gap filling. This work was done by Hamad and his team at Clark University. They were evaluating the foundation model against a baseline model. In this case, was a GAN. So this is an example showing you have cloud cover in a time step. Can you use the foundation model to fill in the missing data? These are some other applications using the foundation model. It was tuned to help in flood detection and burn scars. This is showing burn scars, and then deployed as an inference service. So it can be used by tools, visualization tools and analytic tools, where you can give it a scene and it can do inferencing on that particular image or the satellite image for you. So this is showing our evaluation of the 3 different use cases that we tested out. The top right is showing the performance. You can see that using the foundation model, you have improved performance, overall performance. But what is more interesting are the 2 other figures. The one on the bottom right is showing the amount of label data that you need is substantially smaller than what you would need if you were trying to build this from scratch. And the same thing on the left-hand side is in the compute resources that is needed. You are saving significant amount for people downstream in terms of GPU resources if they're using the foundation model as the starting point to build their particular applications. Some external reviews. I think this was from Wenwen Lee's group from Arizona State. They tested out the foundation model to see whether it can actually generalize over different locations, and they found that it does. So this is a really interesting analysis done by her group there. Some lessons learned in terms of after doing the study was one thing we need to make clear that these models are not expected to outperform all state-of-the-art AI models in every application, but they do provide advantages, especially this notion of using self-supervised pre-training. It allows the model to learn from the data itself, the patterns and that exist in the data. And once it's learned that, then the amount of labeled data required is much smaller, as I showed in the example. And also in terms of the computational cost required to build applications once you have a foundation model. I think one of the things that we did was, we want to make sure that everything that we created was openly accessible. That was the code base, model, weights, data. And we wanted to make sure that it was made available to the community at large who could experiment and test out the model for their own particular applications. This is a really nice email I got maybe a couple of weeks back from a group from Africa called InstaDeep, and they reached out to me, and they took the HLS data and foundation model to build a locus feeding route prediction application very effectively. They said that the model and the data allowed them to do that they were not able to do earlier. And not only that, they were able to basically create tooling around the model, in terms of open source data pipeline and how to use the HLS data, pre-process it into their fine-tuning applications. This is exactly what we had envisioned, that if you build these foundation models for high-value data sets or thematic areas, that would make our data far more accessible and useful for people to build applications and do different scientific research. This is our foundation model roadmap. On the left is the language model side of it. The right table is on the science side of it. On the language model side, we released the encoder model during AGU. I wasn't there, but it was released. It's accessible on Hugging Face. And there are 2 additional models, which is taking the base encoder model and tuning it to calculate encoding, and then also to do passage matching is also being released there. We're working towards having an AI platform to build applications but the platform needs to be tuned for science. It's not a generic platform. How do we support applications for science where the guardrails are built in, where we make sure that we use of the language model is safe, and the training. We want to make sure that we train the community to use these models and the platform effectively, so that we use the right models for the right task. We use right approaches, whether it's through prompt engineering or fine tuning or using RAG. We want to make sure that for different applications we are using the right approach. On the foundation model side for the science data, we are working on a newer version of HLS, which hopefully will be larger and can perform better over temporal timescales. And we are working on a weather and climate foundation model, which I think would be a really interesting. It's a very challenging problem because of the volumes of the data and the complexity and the underlying physics that we have to the model has to learn. So I think one key thing that we have, made sure when we started this work, as I told you, we realized that no one single group can do this, at least for science, do it effectively. I think we need to have an open collaborative approach to build these foundation models for it to be useful for the community. And that can only be done if you have participation from diverse groups, so that you have different perspectives, you have different skills. So we've tried as we've gone along, as we've learned building these models, that we try to engage science experts, the right science experts, right universities, right research labs and organizations who can come and provide support, not only in terms of expertise, but infrastructure, and also engaging with the industry. I think that's where the leading edges right now. We can leverage their expertise, their processes, their knowledge in building these models for science. And obviously, within NASA, everything has to be grounded within open science. I think for AI, it's even more important. We have to make sure that everything that we build is openly available. Whether it's open models, the workflows, the data code, the validation, which is essential. I think having communities set up validation use cases and benchmarks is essential. And I think we have to work towards building trust in AI by providing the right answers, making sure we have attribution, right? We're attributing where the work, the answers are coming from, reducing bias. We want to make sure that we want to make sure the community knows how to use the AI responsibly, understand strengths and weaknesses of each of these models. None of these models are perfect. They all have built-in assumptions. And it's important to learn those assumptions, and that can be done through workshops, documentation. And it's a fast-moving field. I think we have to continuously monitor and assess new techniques that keep emerging that we can leverage and bring into play really quickly, so that we can utilize it within our workflows correctly. This is a couple of slides on my closing thoughts. This was a really nice quote that I found in one of the NRC reports. It talks about the enduring value of the science data. It basically says that once the instruments are gone, what remains are the volumes of data that these instruments have collected over their lifetime, which is for our cases like decades of data that we've collected. And I think with new high data rate missions, the scale will only increase, right? So we have lots of data that we've already collected, and we are going to collect lots of data and new information at an exponential scale. So I think going back to the original starting point of this, like how do we handle this? And I think there is an opportunity here because we are at that inflection point with AI. Can we infuse AI in a way that it can help us handle this problem of scale, both in terms of extracting insights from the data, but also to streamline how we manage data and how we govern data through the life cycle itself. And I think this is my challenge to all of you. I think AI necessitates a forward-thinking perspective on the evolving role of informatics in the future. I think what this means is, how we think of existing processes, policies will have to change, in my opinion, to incorporate AI, to use it effectively. We can't be too tied to our old ways of doing things. We have to think a little bit outside the box in how to utilize it. This is not just looking at it as a tool adoption, but also as a process adoption. So I think with that, I will end. Thank you so much again. Thank you again, Danny, for being so patient in trying to reschedule this.
No problem. Thank you so much, Rahul. And on behalf of all the participants and the informatics section, congratulations and thanks again for coming online with us. We have only a few minutes left, and I'm wondering if anybody has a question for Dr. Ramachandran that we can get in a quick question before we have to adjourn for the day. And certainly this is a great thought-provoking and stimulating conversation, not just from the technical side, but also the philosophical side. And I'm wondering if maybe we can't have you back through the informatics section and host another one of these sort of Q&A and discussion topics. But right now, if anyone has a quick question, maybe we can put that in the, I'll check the questions tab here. And I did share with folks that this recording will be shared through AGU's YouTube channel, but also we'll post it on the AGU Informatics section website, and we'll also share it through ESIP as well. I don't see any, let's see, I don't see any questions related to Dr. Ramachandran's presentation, but thank you, Aaron, for prompting us to remind everybody that AGU session proposals deadline ends in 2 weeks. But if there are no questions, I have one actually that I'm curious, new to the technical side of sort of foundational models and GeoAI, and to your comments about the comparison to sort of these LLMs for societal use, there's a lot of talk about the ethical applications of AI, and I'm wondering if you can comment on that. Does it translate into the georeference frame in large satellite models? Are there things that people will be concerned about in terms of safety and governance and ethical use?
I think yes, actually, it's there are two ways to look at it. I think one is to make sure that people use it correctly, right? I think it's an ethical thing to make sure that people are trained. Everyone is trained correctly to use it. It's not only a few people, a few groups who have the capability of using it. I think the same thing that happens on the language side, those biases can also happen on the geo side too, right? If you think about it, maybe you have observations, maybe the data is collected for certain regions. So you have models that are effective for certain special regions, which may have consequences, unintended consequences that we've not thought about. One thing that is done is, there's sampling done in terms of training these models. So are you sampling correctly? Are there built-in biases in your sampling? That can also happen. So there are things too that you have to think about. I think you cannot, maybe it's not as prevalent as in the language side, but there are implications that we have to consider here.
Yes, and thank you so much, Rahul. We're just a minute over, but I think I speak for everyone when I say congratulations again, and we thank you for your time with us today.
Thank you, Danny.
Thanks, everyone. See if I can now.